Good afternoon, guys. So this is a continuation for our topic on yield line analysis or yield line theory. So we go now focus on the fundamental assumptions we need to consider in the application of yield line theory. Okay. So the first one is that your system must be the material must be elastoplastic or it may exhibit an EPP or elastic perfect plastic PPP. So real line separates slab into plane segments, so able to rotate as such at the unit stage. Okay, so there must be uh, a way on how to subdivide your slabs into separate segments because it cannot rotate freely forming build lines if there's no possibility to separate them into segments. So for number three, elastic deformations are negligible compared to plastic image. Okay, so we need to say that the small deformation theory is evident. So bending and twisting moments are uniformly distributed along the yield line. They are the maximum values provided by the moment strengths in two orthogonal directions. So the guidelines for establishing yield lines, we have five. So I want you to take a look at the video here below. So for number one, yield lines are straight lines because these are axes of rotations at intersections with plane segments. So whenever you have a yield line, make sure that it's a straight line because a segment cannot rotate if there if the yield line is not straight. Okay, so it's very hard to imagine a rotation is an individual segmental rotation if the yield line is not straight. So number two, support edges establish axis of rotation. So here, this support edge here constitute number two, not scenario. So this must be, if I continue this must be an axis of rotation. Okay. So for number three, an axis of rotation will always pass over any column support. So if there's a column support, there must be an axis of rotation whether it is a yield line or not. So it may or may not be a yield line. Just in this case, these column supports here have an axis of rotation, but they are not yield lines, no? And also this one is an axis of rotation. Okay. So for number four, yield lines rotate outward from point of application of the concentrated load. In such a scenario wherein this is the top view of the slab and we apply a point here, always that there is a 100% probability that there will be a yield line rotating somewhere from this point. It can be 1, 2, 3, 4, as many as you can imagine. So for number five, yield lines between positive yields must pass through the axis of rotations. So if you have a two positive yields, or this is a positive yield, so how will you define a positive yield? So a positive yield is like this, okay? So the bending moment is somehow positive. So the deflection delta is directed downward. Okay? So this is a positive yield, while a negative yield is the reverse. So this is a negative yield, the deflection is upward. So here, the tendency for this is to rotate. So this is now a positive yield. edges are negative yield. Okay, so string this one. Okay, so support edges are negative yields and midspan uh, rotations are positive yields. So we can also define support as positive and midspan as, sorry, this is negative rather, and midspan are positive. Okay, so for these positive yield lines, uh, in between the other yield lines, it has to pass through the axis of rotation of the adjacent panel. So if these are the two adjacent panels, this must pass at the negative yield lines there. So there's a point of intersection defined at this point. It's a point of intersection. So it's true with these two segments here, 1 and 2. This positive yield line will pass through this negative yield line. So this is negative, this is negative, and this is positive. Okay. So for the yield line theory for slabs, we take note of the following. First things is to do is to assume a mechanism, because this is the YLA, or is a mechanism method. Okay, so we always have to have a mechanism, or else if you don't have a mechanism of collapse or failure, then you cannot proceed with the yield line analysis. We have to choose the smallest load from the assumed mechanisms or mechanism. If you only have one mechanism, of course that will be your final answer, but if you have several mechanisms, you have to choose the smallest to yield your ultimate capacity. So for slabs with no plastic hinge, uh, for slabs, we do not consider plastic hinge, because plastic hinge are points. No? In beams, we are considering plastic hinge because we are considering point rotation. Okay, while in yield lines, we are considering line rotations or axis. Sorry, we are referring to axis rotation. So yield line patterns depend on the support condition, location, and shape of the panel. Okay, so we actually discussed some few uh, principles or fundamental principles a while ago. So how to solve for yield the how to go over the yield line procedure or analysis procedure is to apply the principle of virtual work, which states that the sum of the virtual work done by the forces in a rigid body is always equivalent to C. So the other method is an equilibrium method, but this is more difficult to apply. Okay, because we are talking here of forces and moments. Okay, so if we now consider a simple beam, again, this is a prop beam, the prop beam that we have been using at the start of the lecture. We may consider the virtual work in this manner. No? So take note that the external work is done so by the forces. Okay, always the external work are done by the forces, and it's simply equivalent to the force times the deformation or the displacement, while the internal force is done by the moments, okay? Or the external or the internal work is done by the moment, equivalent to the moment times the rotation, okay? So in here, we take a look at the external moment now is defined simply by the whole segment. So we do not use a segment by segment procedure here simply because we are using an integration procedure. But if I am to use a summation procedure, I have to cut this into segments. So if I make use of the whole uniform load WU at total on the entire span, I only have to make use of a differential strip, and this differential strip will mean a WX multiplied by delta x then. Okay, so whatever is the displacement at the point x coming from this will give you the deformation or displacement, and whatever W is defined at the point x will give you uh, the force that will give you the internal work, or sorry, the external work. Right? Okay, so simply this is Wx delta x dx. If W is uniform, then we can place W outside because this is constant, and this will be now simply your total deformation, the integral of delta x dx is simply total displacement. Okay, take note that the integral of delta x dx is the area under curve, and work here is simply pertaining to the area or the energy. Okay, if we are looking into an energy interpretation of the said methodology, then this is an energy because of the shaded area. Okay, so the area is simply the area of this triangle defined by the base WU and the height, maximum height, delta. Okay, so for the resisting moments, I'd like to go over the computation of how the resisting moments will be derived. Okay, so for the yield lines at right angle to the reinforcement, so if the reinforcement are parallel or perpendicular to the yield lines themselves, then Mn is simply equivalent to this famous formula. But of course, this is small letter m. This is a per unit width in, say, kilonewton meter per meter. Okay, so note that Mnx is not may not be equal to Mny in general because you can have a different value of As and a different value of your depth on the at the orthogonal direction. No? So the positive Nm may be different from the negative Mn also. So for yield line at angle at a certain angle to the reinforcement, then let's say you have a yield line somewhere here, then your Mn and Mn will be defined in terms of what you call this, a longitudinal and a tangential moment along and transverse. Okay, so along and perpendicular or transverse, longitudinal, tangential. So if I take the moment along the shield, I will only need to make use the projection of MNY and MNX. So MNB multiplied by the total length. Okay, what's the total length? The total length L1 of the yield line is equivalent to MNY. If this is theta, this must be L cosine. This length here is L cosine of theta multiplied by cosine of theta, because this is the component of this M and Y here. Okay, so this is the component. And of course, we have to add the component of M and X, which if this is your theta, it will be a sine theta. And this is also an L sine of theta. So I get now this equation for your M, and since L will cancel out in the equation. Okay, so similarly for the summation moment normal to the yield, I do the same, but here this times I will be having a sine theta, cosine theta, and a cosine theta, sine theta there, because this will no longer be mnx and mny. Okay, so this is x and this is y. Okay, so this is not b, this is d. Correction. And L will also cancel here, such that if I substitute the value of sine theta, cosine theta in your trigonometric identities, this will be equal to 1 half sine of 2 theta. So this is the equation for your M and E uh, in this regard. Take note that when M and X, M is equal to M and Y, M and D is equal to M and X and M and Y, and M and D is equal to 0, then the slab is said to be isotropically reinforced. So let's go down to the steps involved in the ultimate load analysis. So using a possible mechanism pattern or yield line pattern. So this is the yield line analysis or the mechanism method. So first we determine the possible yield lines. So we can have 1, 2, 3, 4. All possible patterns may be assumed, and then we take note of the unknown dimension determined from the result in the smallest value to for each pattern. So for all possible patterns, we always determine the smallest value, because this is will be your ultimate capacity. And for number 2 step, we determine the ultimate load using vertical work, as we have discussed a while ago, and the equilibrium method, as we will be discussing later. Okay. So for the vertical work method, I made here some additional lecture, but this is more applicable when it comes to programming. So when we do programming, might as well make it systematic. So you can use this, or you can use this as your algorithm. So we will not be tackling this in detail, because this is separate the programming lesson that I may be giving you in a separate video. But to discuss to you the basic steps first, we make use of a working equation as a function of your variable a. Okay, so what is your work equation in terms of a? Okay, if you have one pattern, your variable will be one variable. Okay, so per pattern you can make, okay, the number of variables concerned is based on the mechanism. Okay, so this is different from the number of patterns. You may have one mechanism with one variable but different patterns. You can have several mechanisms of different variables with different patterns. Okay, so it depends upon your choice. So if your mechanism and your pattern is a single variable pattern, then we can simply make use of an optimization technique again that I told you a while ago, that is partial derivative of the work equation with respect to the variable of concern is equivalent to zero. So just like what we did in our first lectures. Then we solve for A, and upon solving for A, we can get now the value of your capacity using Greek over. But if you have a lot of independent variables A, B, C, then you have to take care of that by using tree optimization procedure and then make a solution of three equations or three unknowns to get the final set of variables which may be of different patterns. Okay? So for number 4, only the bending moment component M will contribute to the internal visual work. So since the torsion and the shear will cancel out. Okay, so the net virtual work for torsion and shear, so torsion minus shear will be 0. So you don't need to worry about torsion and shear in this regard. Okay, so that's it for the virtual work method. I'll be discussing to you the equivalent or the equilibrium method on my next video. Thank you very much for listening.